Good evening, Divya. Good evening, Jashri. So today, first of all, we will discuss about hexagonal close pack structure. Good evening, Durga Uzma. So this is the hexagonal unit set that I have made on this particular slide. Please make this diagram. And you can see there are 3 layers. 7 atoms are in top layer. 7 atoms are in top layer and 7 in the bottom layer and 3 in between. These are 7, 7, 7, and these are 3. Okay. So these 3, they totally belong to this particular unit cell. Now,
the 3 cells, so 3 atoms are totally belonging to the given unit cell, right?
3 atoms are totally belonging to
the unit cell, you said.
Yeah, these 3, yes.
Okay.
These 3, they completely belong to this particular unit cell. But all other atoms, they are shared. For example, the shape of this one will be half. This one will also be shared with the unit cell, which is just above this unit cell. So the contribution of this one and this one will be half.
Okay.
And what about these one?
6.
Yes. So number of atoms. So there are 12 corner atoms, and contribution is 1/6. And 2 central atoms, face centered one, you can say, contribution is half, and 3 atoms within the middle of the cell, which are totally belonging to this one. So in total, there are 6 atoms belonging to this hexagon.
So can you explain 1/6 contribution?
Half contribution, 3 in total. This one is having contribution 1/6, all of these. And these are 12 in number. 5, 6, 7, 8, 9, 10, 11, 12. Okay. Clear or not? Or should I make the complete diagram?
I'm just confused about the 1/6 contribution. That's it.
I know. That's why I'm asking. Now see. If I try to enclose that particular atom, what has to be done? See, it will be enclosed by 3 hexagonal unit cells because this is making an angle 120 degree. Let us try to understand without making the diagram.
Yes, sir.
120, so it means it will be shared by 3 hexagonal unit cells within the plane, and 3 will be above those cells, 3 hexagonal. So this will be enclosed by 6 cells in total.
Yes, sir.
Let me tell you, what you can do is you can extend this one like this. So there will be 1 cell here. This is 1 cell. This is second. This is third, and 3 above them. Now clear or not? Actually, this line it will be along this one somewhat. So this cell, this is also 120. This is also 120. Clear now?
Yes, sir. It's very clear.
So it means 6 hexagonal unit cells, they will be enclosing each of these corner atoms. So it means contribution of these corner atoms to this particular unit cell, it will be 1/6, and there are 12 of them. Now clear to everyone?
Yes, sir.
Okay. Now, one more important thing. Actually, there are 3 axes A, B, C. If I call this axis as A, let me tell you, this axis as B, and this axis as C, like this. So these 3 axes, they are used to study the structure basically. And here, each of these angles, these are 90, and this one is 120. It is like this, A, B, C. Angle between A and C is 90, B and C is 90, but between A and B, it is 120 degree. Okay? Clear?
Yes, sir.
So now, there is another important thing which is called C by A ratio. But first of all, let us calculate the area of the bottom plane and hence the volume of this hexagonal unit cell. That is more important to us. But first of all, let me write angle between A and C is 90. Angle between and one more important thing. The lengths of these A and B are equal, and they lie in same plane. So A is equal to B, but not equal to C. Clear?
Yes, sir.
Okay. And one more thing. Obviously, they are not going to ask this, but for your knowledge, I'm telling you. It has been found that with these axes, if we associate the Miller indices with the planes like HKL, as we have done with the other crystal structures, then these 3 Miller indices, they are not sufficient to describe this HCP crystal structure. So for this, we use Miller-Brevius indices, not just Miller indices, and they are denoted by HKIL, and that I is nothing but minus of H plus K. Okay. So 4 index, they are needed for the planes in HCP structure, and I is calculated by negative of sum of H and K. HKIL. These are called Miller-Brevis index. But they are not going to ask you, but still, you should know this, that Miller-Brevis index, they are different from Miller indices. And how to get them. Means if you know HKIL, you can calculate HKIL by using this formula, I is equal to minus of H plus K. Clear?
Yes, sir.
Now, let us calculate the area of this bottom hexagon. Now, in order to calculate the area, what we can do is, now see here, I said this is A, this is A, this is also A, so this is an equilateral triangle, this one. So, if you make a perpendicular from the vertex to the base, then each of these angles will be 60 degree, 30 degree, isn't it?
Yes, sir.
Please check.
Yes, sir.
And what about the area of this equilateral triangle?
2, 3, 4 by 8 square.
Root 2 by 4 side square, and there are 6 of them, there are 6 of them.
Yes, sir.
So, area of triangle AOB, because it is an equilateral triangle with each side equal to A, so area will be root 3 by 4 A square. So, area of the base, and base is hexagon, and it is composed of 6 such triangles. Please count. 1 triangle, 2 triangle, 3, 4, 5, 6. Clear? This 3 root 3 by 2. And what about the volume of unit cell then? If I multiply this by height, that is C, it will be area of base into height. And height is C, that is C axis. So it will be 3 root 3 by 2 A square into C. And we check. Clear? Please. Is it clear or not?
Yes, sir.
Now, there is another important quantity which is called C by A ratio. And C is this. This complete length is C. And because this atom it lies midway, so this distance will be C by 2, isn't it?
Yes, sir.
Yes, sir.
So if I join this by this atom, then the diagram will look like this, little bit. And what I have done in the earlier case, in the diagram on the next slide, I have made a diagram like this. Now you see, you will be able to understand this diagram. This is the complete triangle AOB, you can see. So I have drawn the perpendiculars from the opposite vertices, from O and from E. These are the perpendiculars. Okay? Means this is the point of intersection of these altitudes. Means the centroid. You remember this is the point, this point we call as centroid. Okay? Here?
Yes, sir.
And centroid, it divides the median or the altitude in this case, you can say, in the ratio 2:1. Then what is the ratio between AX and AY according to you?
AX by AY equals to 2 is to
2 by 3. 2 by 3, no? AY is total.
1. AY is total, right?
AX is to XY will be 2:1, no? But AX to AY will be 2 by 3. No? If you write like this, then it will be 2 by 1. No? But AY is AX plus XY. No? Clear? Please check. And what is AY? What is the altitude in equilateral triangle with side A? Anyone? Root 3 by 2. So it is A by root 3. Is it clear to all? Please check.
Yes,
Huh?
sir.
Now, coming back to the diagram. So we have calculated this AX. Rest everything is known. Now this distance, this is A. This is C by 2. This you have calculated. This is A by root 3. This is the same triangle that I have made over there. Okay. Now in triangle AZX, we can make use of the Pythagoras theorem. Hypotenuse square equal to perpendicular square plus base square. Clear? Now, in right angle triangle AZX, we have it is AZ square equal to AX square plus ZX square. It is A square, AX is A by root 3 whole square, and it is C by 2. And from here we can calculate C by A ratio, which is a famous quantity in this particular structure. So what you can do is, you can combine the terms containing A on one side, and then the terms containing C on the other side. So it will be like 8 by 3 equal to C square by A square. So it will be 8 by 3 square root C by A, and this is very important. And at some places it is directly written. They don't give the proof for this one. Please check. Clear? It's easy, huh? If you do it carefully, it is very easy. Just the Pythagoras theorem and the concept of the equilateral triangle and that of the centroid. Nothing else. Clear to all?
Yes, sir.
Yes, sir.
So now let us try and calculate the packing fraction, because we have already calculated the number of atoms per unit cell and the volume also. Okay. So what we need to do is we just have to calculate the volume occupied by the atoms, and we have to divide it by the volume of the unit cell that we have already calculated. But before that, please note down nearest neighbor distance. Actually, those atoms, they are touching along the edge. A is equal to 2R. Okay. Now packing fraction. How to calculate the packing fraction? Volume occupied by the unit cells, volume occupied by the atoms, and atoms are 6. Na? So 6 into 4 by 3, and volume of unit cell was 3 root 3 by 2 A square C. Now it is 8 pi. R is equal to A by 2. Na? So this 8 will get cancelled with 8. A square also get cancelled with A square. And we are left with 2 pi A 3 root 3C. And what I can do is, can I write it as, and now we can substitute for C by A ratio, which is 8 by 3. And root 3 will get cancelled. So it will be 2 pi by 3 root 8. And root 8 is nothing but 2 root 2. So 2 also get cancelled. So pi by 3 root 2. Please calculate the value. And it will come out to be equal to packing fraction.
0.7%.
Same as FCC. So FCC and SCP, they are the most densely closed packed structures. Okay? Clear?
Yes, sir.
So this was everything about HCP structure. Now, one important point. Most of the metals, they try to crystallize in the FCC form. Most of the metals that we come across in our daily life, for example, iron, copper, etc., they all crystallize in FCC because it is the most densely closed packed structure. Okay? Now, one question. How many cells are there in an aluminium foil, 0.005 centimeter thick and side? Now I will tell you the meaning of this side 25 centimeter square. What does it mean? It weighs 0.0085 kilogram. How many atoms are present? C option. C part we can see. How many atoms are in each unit cell? Given atomic mass of aluminium 26.9 kilogram, or gram per mole. If you want to write per mole, it is 26.9 gram. You can write it this way also. Okay. Now, first of all, let me tell you what is the shape of this foil. Actually, the foil is like this. Thickness is given, and then it is given that side is this much. So side 25 centimeter square means it is a square with side 25 centimeter, and then the thickness is 0.005 centimeter. So it is a cuboid. Okay, so this is the diagram of the foil. Clear? Side 25 centimeter square means this is a square with side 25 centimeter, and then the thickness is given. Now, how we can get the number of cells in this aluminium foil?
Find the total volume of the foil, divide by the volume of a unit cell,
Yes.
divided by A.
Yes. So volume of foil divided by volume of unit cell. That will be the number of unit cells in this particular foil. So please calculate. Number of cells in the foil equal to volume of foil by volume of unit cell. So please solve this. Yes, what is the final answer? So it is 25 into 25 into 0.005 in centimeter cube, and that was A cube, that is 0.405 into 10 to the minus 7 cube. Then if we convert it into centimeters, so what is this value according to you?
So it's 10 to the minus 9, I think 0.205 10 to the minus 9.
10 to the minus 9 meter, huh?
7. Okay, centimeter. Yeah, okay. I mean,
Because other values they are in centimeter, so it's easy to convert it into centimeter rather than converting all of them into meter. You can do it other way also by converting them into meters, those foil dimensions. One and the same thing. So what is the final answer? Nobody calculated till now?
Sir, 47.04 into 10 power 9.
This much?
Yes.
Now the B part is. Now the B part. No voices coming from your side. Yes. You wanted to ask something, Tanya?
No, sir, about Minecraft.
Now, the weight of this file is given, and they are asking how many atoms are present. And for this, we need this information, this atomic mass. Okay. So what we can do is, we know the number of atoms within this mass of the file, and then we can calculate within this mass. Okay. So what we can do is, 26.9 kilogram of aluminium contains. So I have converted the mass into kilogram. So accordingly, the Avogadro number will also change. Avogadro number will become 26 now. If it is in gram, then the Avogadro number stands for 23. Okay. So 1 kilogram of aluminium contains. Okay. And how much mass is given? 0.0085. So then 0.0085 kilogram of aluminium contains. So please calculate the number of atoms now.
So 1.9 into 10 power 20.
1.9 times per 23. Now in the C part, we have to calculate the number of atoms in each unit cell. And for that, we can divide the number of atoms in the file by the number of cells in the file. So now you are having both of them. Otherwise also, because if it is a FCC structure, there should be 4 number of atoms per unit cell. So
Yes, this directly given.
when you actually calculate this, you will find this. And this is further verification of that effective number in FCC. Okay, noted this one. So this will be 1.9 times per 23 and 4.7. How much? Exact value. 19 by 4.7. 4 point something. This will be, I think.
4.04.
Okay, so but I think if we take that 4.704, it will be like exact number. Because I made some approximation over there. So it is nearly equal to 4. Clear to all? So this is how we can calculate the number of atoms, number of cells, etc. Now, let us see. I told you about the distance also, DHK. Yes. So now we can discuss the questions based on that. Distance also. But first of all, this question is there from IIT Jain, and I need to discuss this. And let us see how many of you remember this. The ratio of second neighbor distance to nearest neighbor. In an FCC lattices, and the options are 2 root 2, 2 root 3, root 2. And this is from IIT Jain 2008. So what is the answer? What was the first nearest neighbor distance?
So root 3 by 2a.
First nearest neighbor distance. And what is second nearest neighbor distance? Anyone? First and second.
A by root 2, sir.
A by root 2.
First.
First. And what about second?
A, sir. Correct answer, D, sir.
So can I call this as D2 and D1 just to make the thing easier? Okay.
Yes, sir.
Easy. That was in BCC. Someone said root 3 by 2a, I think.
Yes, sir.
I think it's a BCC lattice, that's why I said.
That is in BCC. Okay. That is not in FCC. In BCC, first nearest neighbor distance is root 3 by 2a, and second is a. If it would have been BCC, then root 3 by 2a and then a. It's like that. Yeah.
Yes, sir.
Now. First of all, try to understand the question. This is one cell. This is adjacent cell. Okay. And then there are atoms within the body center. One atom is here within the body center of this unit cell, and another is here. And now you can see there is some gap here, here in between these two. Okay. So if I place some atom or sphere here, then what will be the maximum radius of that sphere? That's what they are asking. So diagram is clear. Actually, I have taken two adjacent BCC lattices, and atoms are present at the centers of those BCC lattices. So I'm considering the atoms at the center within the body center. So if we see the atoms present at the body center of each one of these unit cells, then obviously there will be some empty space between those two body centered atoms. And if you place any sphere between those two atoms, it will be having some finite radius. No? So what is the max radius? Now let us suppose the radius of this one is R. So obviously this one is also R, and this one is small r. Okay. Let us suppose. Then the center of this sphere, it will lie at the edge of the unit cell. No? See, I have made a line for that for the reference. Center, because half of this sphere will lie in one unit cell and half of it will lie in another unit cell. So center should be at the edge, no? Isn't it? Please tell.
Yes, sir.
Yes, sir.
What is the distance from center to the edge? It is a by 2. Distance from center to edge. It means if we have a look at the diagram, then r plus r is a by 2, no? Because center of one sphere is at the edge and center of other is at the body center, and the distance between the body center and the edge is a by 2. And what is this r equal to? Or this A equal to, sorry, in BCC, because this is BCC structure, and there is relation between this A. A is 4r by root 3, no? Isn't it?
Yes, sir.
And capital R is the radius of the normal atom, so that's why I've taken capital R. So r plus r is 2r by root 3, and now I can calculate this small r in terms of this capital R, and it will be like 2 by root 3 minus 1 r, so it will be 2 minus root 3. Can you solve this for me? So this way we will get to know the size of this sphere. And why it is called interstitial sphere? Because there is a void between these two body centers, and the void is called interstitial site or interstitial void. That's why it is called interstitial sphere. Because this sphere has to be put at the interstitial site or void. And please check, is this value coming out to be 0.155 r? And you can see this,
Yes, sir.
this void is very small, because the radius of the sphere, max radius of the sphere which can be placed at this site, it is only 15.5% of the normal radius. That is 1/6, almost 1/6 of the size of the normal atom. Okay? Clear?
Yes, sir.
Now another one of this kind. Find the So now we are given the FCC structure, and if we consider the atoms present at the face centers of the opposite faces, then obviously there is some empty space between them. No? See, now we require only one unit cell because we are talking about the face centered atoms. So one atom is present over here, other is present over here, and there is an empty space. No? You can see in between them. So suppose we place a sphere with radius again small r. This is capital R. So again this distance is going to be a by 2, no? Because the center of this one will lie at the body center, because the structure would be symmetrical. No? Because the centers of both the end spheres, they lie at the edges. Clear? Please check.
Yes, sir.
So again, but now the situation is different. No? Now it is FCC structure, so A is not equal to 4r by root 3. What is the value of A in case of FCC?
Sir, 2 root 2 r.
So small r will be equal to root 2r minus r. So it will be root 2 minus 1 into r. So 1.414 minus 1. So this void is bigger, you can see. It is having the radius 41.4% of. This one is bigger. Clear?
Yes, sir.
So now let us discuss something about the graphene structure. That is also an important part, because not much literature is there on graphene if you have a look at the books. So that's why the students, they find it very difficult to understand this graphene structure. But there is nothing difficult about this structure, as you will get to know by this discussion. But you have to listen to me carefully, okay? So this is the graphene structure. So if you want, you can make this diagram, but otherwise you will be getting this PDF if you are finding this difficult to make this diagram. So these are the hexagons actually. Okay. Now, the first very important thing about this structure is, now see here, if you have a look at this particular, this is made up of carbon. All these are carbons. All these are carbons. If we have a look at this particular carbon atom, there is a carbon atom present to the right of this one, and there is no carbon atom present to the left of this one. But if I consider this particular carbon atom, there is no carbon atom to the right of this one, and there is a carbon atom to the left of this one. It means the surroundings of this carbon atom and this carbon atom, they are different. Means they do not behave in a similar manner. Okay. It means in this scenario, we will say that both the carbon atoms, they are different. Although these are carbon-carbon, but because their environments are different, so they behave in a different manner. And for the same reason, it will be a 2-atom basis. So there will be 2 carbon atoms per unit cell for the primitive graphene unit cell. But otherwise, in all other cases, we say that primitive unit cell, it is having the atom, 1 atom per unit cell. But here, because of the different nature of these carbon atoms, there will be 2 of them. So that's why we call it is having 2-atom basis. So if we call these atoms to be of A type, these carbon atoms to be of A type, these to be of B type. So nothing over here, nothing over here. Okay. So as atoms A and B do not have identical surrounding, so both cannot be the lattice points, first of all. So one of these is lattice point actually. So in order to make the lattice, what we have to do is either we have to combine the atoms of type A only or atoms of type B only. So only AA atoms or BB atoms. Only then the crystal structure will be regular, repetitive one. Okay. If you join A and B, then the symmetry will be broken as soon as you move from A to B or from B to A. Which is non-primitive. We will get a hexagonal unit cell which is non-primitive. Okay. Now let me tell you how we get this hexagonal unit cell. Now see here. Suppose I'm joining all the atoms of this kind. This I named as A. Na? A. Let's mark AA. A. This is also of A type. This is also of A type. This is also of A type. Like this. Clear? So kindly join these together. This. 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 So you can see that we end up getting a big hexagon. So this is the unit cell that I was talking about, that I've written. I have mentioned in this particular slide that we will get a hexagonal unit cell which is non-primitive. So obviously it is non-primitive now because it is containing a lot of atoms. These four are totally belonging to this one. And there are atoms at the corners also. Clear? Clear or not?
Yes, sir.
Yes, sir.
This is the unit cell which is non-primitive. Now, what is the unit cell which is considered to be as primitive in this case? For that, what you have to do is this one. This red one that I'm making. This is primitive unit cell. This is primitive unit cell. And how many atoms are there in this primitive unit cell? You will see there are two of them. Two atoms. This is a two atom basis. And how two atom basis? You can see this atom is of B type and all these atoms they are of A type. This is of A type, this is of A. So one A type atom and other B type atom. So one of each kind is there. Okay, please check. Clear or not?
Yes, sir.
Number of atoms per unit hexagonal cell. Can I write per unit hexagonal cell?
6.
Because we are considering two unit cells, non-primitive and primitive. So number of atoms per unit hexagonal cell, that is non-primitive cell. Let us first calculate the number of total atoms present in the non-primitive, that is the hexagonal cell. So how many atoms are there? These four, they totally belong to this unit cell. And what is the contribution of these to other atoms? There are six of them.
1 by 6 each.
Is not 1 by 6?
6. So 1 by 4.
No. It is a layered structure. It is a 2D structure, graphene. It is not a 3D structure. 2D structure. Now what is this angle? 120. So it will be shared by 3 of them. That's it. Clear? 1 by 3. Sorry.
Okay, sir.
Because it is a layered structure. Na? Graphene is 2D structure. Let me write here. Graphene 2D structure. So it is layered structure only. It is not the 3D structure. So there is only one layer that we are able to see in this particular slide. Okay. So each atom it will be shared by nearby 3 cells. Na? So contribution is 1 by 3. That's it. It means therefore number of atoms per unit primitive cell. How many atoms? There are 3 primitive cells within the non-primitive cell. Na? See, this is one. Let me highlight. This is one. And there will be 3 of this kind if you find them carefully. Let me show you. If you join this will be second one. This is first one. This is second one. This is third one. Exactly identical. Clear?
Yes, sir.
So because there were 6 atoms corresponding to the non-primitive one, and the non-primitive unit cell, it consists of 3 unit cells. So number of atoms per unit primitive unit cell, it is 6 by 3, that is 2. 2, one of A type and one of B type. Okay, so this way things are more clear rather than just writing the number 2. That is one of each kind, A type, B type. Clear? Please tell.
Yes, sir.
Now, let us calculate the area. Because it is 2D structure, na? Let us calculate the area of the primitive unit cell and the non-primitive. So if we are able to calculate the area of this non-primitive one, so then by dividing it by 3, we will be able to calculate the area of the primitive one also. So how to do that? Again, I will be making the same diagram. because otherwise that particular diagram, it will be complicated one for you and you won't be able to understand. I'm again making the same diagram. This one. Now, in order to calculate the area, what can be done is, please join these two together and draw a perpendicular from this particular rectangle. And you can see this is a big equilateral triangle. This one, the red one. So one big triangle, let us call this as big triangle, and this one is small triangle. So there are three small triangles and one big triangle, isn't it? Yes, please.
Yes, sir.
So now can you tell me what is this distance? This distance particular. What is the area of this small triangle? This is a by 2, na? Because this total distance was a. This is a. This is a. Okay. Then this will be a by 2. If you name this triangle as P, Q, R, S, then what will be PR according to you? What is PS first of all? What is PS? In right angle triangle, PQS, what is PS? PQ square equal to PS square plus QS square. This is A square. PS we have to calculate. This is A by 2 square. So A square minus A square by 4. So it is 3A square by 4. So PS is root 3 by 2A. Na? And PR is double of PS. Na? So it is root 3 by 2A. So area of small triangle, it will be half into base into altitude. Na? Half into PR into QS. Na? Half into root 3A into A by 2. Na? Please check. Clear? Is it clear or not?
Yes, sir.
Yes, sir.
Now, what is the area of big triangle? What is the side of big triangle? PR is the side of big triangle. Na? So big triangle is an equilateral triangle. Na? Each angle is 60 degrees. Please check. And each side is also root 3A, obviously. So area of big triangle. I'm
3 by 4.
writing it here. Area of big triangle. Can I write it on the next slide? Because there is less space. Na? Area of big triangle. It will be root 3 by 4 side square. Na? So area of hexagonal unit cell. It is 1 times the area of big triangle plus 3 times area of small triangle. Na? Isn't it? Please check in the diagram. Clear or not?
Yes, sir.
Area of small triangle was root 3 by 4.
Right.
So it is 3 root 3 by 4, 3 root 3 by 4. So in total, it will be 3 root 3 by 2 square.
Yes.
So what will be the area of primitive unit cell then? So there were 3 of them in one non-primitive unit cell. Na?
Yes.
So it will be
Okay.
a third of the area of non-primitive unit cell.
Okay. 3 root 3 by 2A square.
So root 3 by 2A square. Na? Now please check everyone. So now I think you can get me the packing fraction because you know the number of atoms and the area. So either you can get the packing fraction by primitive cell or by non-primitive cell. It will be one and the same thing. So please get me the value. Packing fraction. Packing fraction and number of atoms per unit area. These two things you can calculate. Note it from this slide, everyone. Everything noted? Yes. Have you noted everything from this slide?
Yes, sir.
So number of atoms per unit area. So I'm calculating these quantities from the primitive unit cell. So there were 2 atoms in primitive unit cell and the area was root 3 by 2A square. Na? So it is 4 by root 3A square. So packing fraction. Again, for the packing fraction, I will use the primitive one. So there were 2 atoms and the area of each one is pi r square and then root 3 by 2A square. And how is A related to R? How is A related to R?
Say 2R.
2 root 3R. 2R is A dash. It is not A. I will tell you. So R square will get cancelled. 1, 2, this 2. So pi by 3 root 3, I think. Pi by 3 root 3. Na? How much? 4. Please check. Now, going back to the diagram, let me tell you how it is 2 root 3R. Is it 0.604?
Yes, sir.
So going back to the diagram, this is not the this one. Now, this is the usual hexagon. Now, I think I can discuss from. Let us discuss from this one. I have joined these two together like this. So according to you, which of these atoms they are touching each other? These two or these two? Which two? This or this? They will be touching, na? Because they are near to each other than these two. Isn't it?
Yes, sir.
Yes, sir.
This you are representing by A. So it means this will be less than A. Na? Now what is this value? I think you can calculate this one. Because you know this angle. Na? Okay. What is this angle? This is 30 degree. Na? If you draw a perpendicular over here, then what is this value? This base is A by
30, it's 30 degree.
it is A by 2. So this will be equal to A by root 3, na, I think. Please check. Because base is known, you want to calculate the hypotenuse. Na? So cos 30 will be A by 2. Let us name this as XYZ. Okay. So it will be like XY by XZ. So I want to calculate XZ. So it will be XY by cos 30. So XY is A by 2. Cos 30 is root 3 by 2. So A by root 3. Na? This is equal to 2R. A by root 3 is 2R. Now I think it is clear. So A is 2R root 3. Okay.
Yes, sir.
Clear to everyone?
Yes, sir.
And if somehow in the examination you are given that this distance is A, so then accordingly modify this one. They may change the symbol. Na? Means this side is root 3 times this distance. If this is A, then this will be root 3A. Na? Okay. Clear? Means if this is A, then this will become root 3A. Na? Clear or not?
Yes, sir. Yes, sir.
So you have to take care of this in the exam. Kindly don't go by the direct values. So be careful. So now is it clear? The packing fraction.
Yes, sir.
Okay. Now let us discuss one question. A simple cubic crystal with lattice parameter AC. ATT means tetragonal over here. Means this is the relation between the tetragonal lattice parameters and the cubic lattice parameters. So you have to use that DHKL formula. This is the hint from my side. DHKL formula. Please solve this and give your answer in the chat box. Yes. You have to calculate T101. Let me give you the formula first. In case of, can we write the general formula so that it can work in both the cases like this? Okay. So now, in case of cubic, all are equal to AC, ABC equal to A cubic. So for cubic, A equal to B equal to C equal to A cubic. So D101 cubic, it will be 1 square, 0 of course. So AC by root 2. For tetragonal, it is given that A equal to B equal to how much? Root 2 AC. And AT, BT, and CT is 2 AC. So D101 tetragonal, it will be like this, 0, this now. So this will be 1 by 2 AC square, 1 by 4 AC square. So it will be 3 by 4 AC square. So it will be like AC into 4 by 3. So 2 AC by root 3. Na? Please check. So now we have to get the ratio. Cubic by tetragonal. So divide 1 by 2. Divide 1 by 2. Please note down from this slide. And let me know if you have noted. Please let me know.
Yes, sir. Noted.
So dividing 1 by 2, because we have to get the ratio of cubic to tetragonal. 1 by 2. So it is D101 cubic to D101 tetragonal. So cubic is like AC by root 2 and tetragonal is 2AC by root 3. So it will be root 3 by 2 root 2. So we can write it in this manner. So this is the answer. 3 by 8 square root. So C option. Please check.
Yes, sir.
Done, everyone?
Yes, sir.
Next one. The total number of sodium ion and chloride ions per unit cell of sodium chloride is 2, 4, 6, 8. So let us see who answers first. Only in the chat box. No, Ishali, it is wrong. Only one answer is there. What about others? Yeah, very good, Abhay. Jayashri. Kanaya, it's wrong. Very good, Tamya. Just think about it carefully. No, Sameshwaran. Kindly read the question carefully and then try to answer it. Total number of sodium ion and chloride ions. You guys are not reading the question carefully. It means you are cramming the things. What we have done in the class. Yes, very good, Amit. Very good, Arun. They are not asking you the individual sodium and individual chloride ions. Total number. What is the total number of sodium ion and chloride ion? It is very simple question. No, Ishali, again wrong. Answer is 8. As there are 4 sodium ions and 4 chloride ions per unit cell. So total is 8. Okay. Clear? Next one. These things should be at your tips now. So packing fraction has to be calculated. So R1 by R1 plus R2. R2 by R1 plus R2 whole cube. D is 2 pi by 3. So we actually derived this formula. Do you remember? Nobody is speaking up. What happened?
Yes, okay, right.
R1 cube, R2 cube. So 2R1 plus R2 cube. So now Vishali is very quick to pass upon this option. Yeah, of course, your answer is correct this time. Very good, Vishali. Jayashri, Siali. So girls are very quick this time. Very good, Abhay, Kanaya, Akhilesh, Ritika. Yes. Others, very good, Ramdhyal. So in the similar manner, they can ask you about that zinc sulfide also. We derived that formula also, na? And of course that diamond one also. Okay. So all those formulae you should remember. They may be asked in this format in the exam. Very good, Amit. Clear to all?
Yes, sir.
Yes, sir.
So now you can try various questions based on this crystal structure chapter. But of course, we have discussed each and everything from this chapter. Because questions from this chapter, they are basically based upon the things that we have studied. They are the theoretical questions or the ones based on the Miller indices and all, or DHKL that you have seen. Okay. So tomorrow we will start with the reciprocal lattice part. Okay, students?
Yes, sir.
That's all for today. Okay. Bye-bye. Take care.
Thank you, sir.
Thank you, sir.